Okay, here we continue with our chapter 4, and now we have another example of quantum dynamics, which is the famous piecewise constant potentials depicted here. It's clear what the meaning is, right? As a function of x, as a function of space, the potential is constant in some region and abruptly moves to another value and remains constant, and so on. Okay, so these are the kind of potentials that are very useful as toy models. And well, we're going to see on both on the PowerPoint slide and also a little bit on the whiteboard how to solve these potentials in quantum theory. So essentially there are two steps. There is, we solve the Schrödinger equation in each region, here, 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 and there, and then we connect the pieces. Okay? So let's go to the first step, which is to solve the Schrödinger equation in each region. So now I have a region in which the potential is constant, fixed at a given value Vj. So the Schrödinger equation, or better said, the eigenvalues of the Hamiltonian will be given by that equation there, right? And now again, Vj is a constant now. So this equation has the form d square x psi is equal to something k square of psi. And then it depends whether, so and this k square will be this 2m over h bar square Vj minus e. And now it depends, right, on whether this number is positive or negative. So if this is positive, if k square is positive, then we have the equation that of exponentials. If k square is negative, it means it would be there would be an I. So essentially, yeah, then this would be the equation of sinusoidal functions. Okay, so that's what we are going to see now on the slide. So indeed, if the energy, if we are looking at an energy that is smaller than Vj, something below the potential level, then the solution, so then this k square is positive, and the solution will be a sum of exponentials. Of course, it can be exponential positive or negative. If E is larger than Vj, so if we are looking at a solution that is above the potential, then this k square is negative, so there is an I factor, and the psi, the wave function, will be a superposition of complex exponential or of cosine and sine. A and B in both cases can be complex numbers, right? So this is pretty clear, right? Of course, A and B has still to be determined. How we are going to determine them? By connecting the pieces of the wave function. That's the second step. First of all, let me remind you that k in both expression is defined as this expression, where Vj minus E is absolute value, right? That's what we have written here. So in each case, we have two linearly independent solutions. You can take these and that, or cosine and sine, these and that, or cosine hyperbolic, sine hyperbolic. And now we have to connect the regions. So let me give you just an example. Here would be an example in which we have an energy that is sit here between V2 and V3. So on the side of V2, the energy is above the potential, therefore it's a sinusoidal curve. On the side of V3, the energy is below the potential, therefore it's an exponential curve. And the connection, the rule for the connection is that both the function and the derivative must be, the first derivative must be continuous at that point. Right? So the function is continuous and also the derivative is continuous. That's the rule of the connection. And well, also that would be an example here where we can find a connection. And this would determine the coefficients A and B of the wave function through these two equations. Now let's see what can happen in practice. So here is again a, well, generic potential. Here is energy. Right? But first of all, if I look at an energy that is below the bottom, there can be no solution there. Why? Because below an energy level, the solution should be real exponentials. But there are only two possibilities here. Either the real exponential as a positive factor, and then it explodes at plus infinity, and it's clearly not a normalizable solution, or it has a negative factor and it explodes at minus infinity. So it would also not be a normalizable solution. So there cannot be any solution, any eigenvalue of the Hamiltonian that is below the global minimum of the potential. So let's not look what happens down there, there's nothing. Now, the other interesting boundary is not so much the global maximum, but is the maximum at infinity, so the boundary at infinity, so that one, V5. So at this stage, you see that at least on one side, the potential is open, if you want. So if you're in that situation, this we are going to, it can be proved. Huh? So these I'm just making statements. This one I'm not going to prove explicitly. It can be proved. So if we are an energy that is above, well then all the energies are possible. The spectrum is continuous. They are not proper eigenvalues. It's one of these continuous spectrum, like the spectrum of the position operator. All the energies are possible. It's represented here. And what kind of states we have, we are going to see it later. They are called diffusion states. But you can imagine already, right? On this side, there might be still some exponential thing, but on this side, it will be sinusoidal functions. Again, not exactly normalizable, but not normalizable, not in a disastrous sense, like an exponential here. It's not normalizable in the same sense as the delta function or the plane waves are not normalizable. So it's one of these pseudo vectors where you have to be a bit careful what to do with them. Now, what happens in between here? So here we are in a region, as you see, where at infinity, at x infinity, x minus infinity, and x plus infinity, we are below the potential. So here, there will be exponential tails, decaying, so that's fine. What happens in the middle? Well, here it turns out that the eigenvalue equation is really not trivial, in the sense that there are just enough many boundary conditions to fix uniquely the values of A and B, the different A's and B's, of these pieces of the wave functions. So which means that we will have discrete solutions. There will be some energies, here of course is qualitatively drawn, I didn't bother making the calculation exactly for this particular potential. There will be some values that are acceptable energy levels, so there will, which means that are eigenvalues, proper eigenvalues of the Hamiltonian. The eigenvectors will be proper eigenvectors, normalizable. And for all the other values, the solution is just not there. So these would not be solution of the eigenvalue equation for the Hamiltonian. And these are called bound states, because it describes essentially a particle that is trapped in the potential. Okay? So this is the qualitative study of this kind of potentials. Again, this one I sort of proved, that one I'm not going to prove, and this one we are going to see examples. Let me do the qualitative plots of the stationary states for every energy level, and please notice how the value of k changes between the. So for instance, okay, we are down here. Well, down here we are going to have real exponential, complex exponential, real exponential, complex exponential, real exponential. And again, here we can make it fully decaying. So e to the ikx, that doesn't explode in minus infinity. Here we can put it at fully decaying, e to the minus kx, that decreases at plus infinity, and in between, well, there's a connection here. I'm sorry that my drawing skills are not so good, so I didn't really convince you that this derivative should be continuous, but all the derivatives should be continuous here. Okay, we go a bit above. If we fix our energy level here, well then we are above all this structure of the potential. So there is real exponential, all the kind of complex exponential or sinusoidal, and again real exponential. However, notice here the frequency, again my drawing is a bit sketchy, but the frequency changes here and here. Here is oscillating faster than here. Why? Because we are higher than here. And you see the K, right? The K increases with the distance from the potential. So here it oscillates faster than here and also faster than here. Because again, we are higher with respect to the level. Here, in principle, we should oscillate faster than here and less fast than here because, again, the level is here. Now, if we go to the first kind of diffusion states, if we are up there, then we have real exponential, and then all the way they are sinusoidal functions. Again, with this behavior, that this is more frequent than that, is more frequent than that, is more fast oscillating than that. Okay? Again, here, don't misunderstand this. So this is, again, is going to be a sinusoidal function. It's not going to be a decaying exponential. So this continues forever at that level. And then, of course, if we are above everything, like, then, of course, again, same behavior. I will not repeat it again. Less, smaller frequency, much higher frequency because the potential is done, and so on and so forth. Right? So this is the kind of qualitative plot. Quite often, I am not sure yet, I have not yet prepared the final exam, quite often a qualitative plot like that might be asked in the final exam. Certainly if you pick up this topic in the Viva, you will have to show a qualitative plot like this to understand again that the energy, the speed of the oscillation increases when we go away from this. Actually, by the way, I didn't say, but it's the same for the exponentials, right? So this exponential decays faster than this and faster than that because it's farther away in the negative direction from the value of the potential. So in both cases, right, the K square in absolute value increases by going farther away from the level of the potential. Okay, now I'm going to make a very important remark that is often a source of confusion, especially for those who don't really master Fourier transforms. And the remark is like this. What we have just described are the stationary states. Even if we call them, some of them diffusion states, those up there, they are not moving. There's nothing moving. These are eigenstates of the Hamiltonian. They don't move. So how do you describe a particle that moves? Well, again, think about it. Think again about your theory of Fourier transforms, right? A wave packet is a sum of, let's say, typically plane waves, right? What would you have to do in order to describe something that moves? Well, the usual thing, right? What is the usual thing? Decompose your initial wave packet on the eigenstates of the Hamiltonian, those guys, apply the typical phase and see how it evolves. Okay? So that's very important to keep in mind that really, again, these objects that we are going to compute here are not moving particles. These are the eigenstates of the Hamiltonian. The moving particle, the principle is clear. It can be done with mathematical or similar tools. Analytical is a kind of a painful thing to do, so we are not going to do it. And I'm not also not going to ask you to do it for with numerical tools, but if you want, if you are keen on that, there are even applets out there. There are examples in Wolfram websites or whatever. You can try. You can even ask your seniors. Some of my predecessors teaching quantum mechanics used to give these as a test to use Mathematica to simulate the evolution of a wave function. I'm not going to do that, but that's the idea. Okay, so please keep in mind what we're going to study are the stationary states, not the. We're not going to give an example of something that evolves. Okay, now at this point, I want to do two examples. The first example, however, I will do it at the whiteboard, is the infinite potential well, and then I will come back to these slides for the second example, which is the finite potential well. So let's see if I can switch off all these things. Success. I have to switch on some lights, sorry for that. we are going to do what is called the infinite potential well. So what is a potential well? A potential well is just this guy. And then we are going to put, can put this value at 0 and this value at v. And now this is the example I'm going to deal with in the slides, in the PowerPoint slides. Now at the whiteboard we are going to do the case where v goes to infinity. So normally we represent these like that. And it's understood that, so essentially it's understood that outside there the potential is infinite. What does infinite mean? Of course, it doesn't really mean anything, but it's the limit in which this particle is trapped very, 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 very deeply. Right? There's very little chance that it can escape. And for mathematical simplicity, we just set it at infinity so that we can do the calculations very easily. So this potential is V of x is equal to what? Is equal to 0 for x between 0 and a. So, and infinity otherwise. So of course now this is in my x direction, this is the value a and this is the value 0. Great. So here it's mathematically very simple, but at the same time there is unfortunately a slight deviation because of this strange infinity from the behavior, from the rule that I gave you. Okay, so we'll see soon what the behavior is. So let's apply our recipe. So the step number 1, let's take another color, if it works. Step number 1 is to solve the Schrödinger equation or find the eigenvalue in each region. Right, so I have 3 regions. We have region 1, region 2, and region 3. Okay. Now, however, in this case, the solution in region 1 and region 3 is kind of trivial because you have this equation, but the potential is infinite. And we are at an energy that obviously, wherever you put your energy, this energy is below infinity. So you have exponential that goes down infinitely fast. So which means that the wave function in this region is strictly 0. So psi 1 of x is equal to psi 3 of x and is identically 0. Now what about psi 2? Well, psi 2 now, wherever we put our energy, will be above the potential because we are not going to go below. We know that below there's no solution. And so it will be a sinusoidal thing. Psi 2 of x, and for convenience I will write it like this. A sin of kx plus b cos of kx, where k will be equal to that. Square root of 2m. Now, so v is 0, and I have to take the absolute value, so it's just e over h bar square. Okay, that's the first step. So here in between, we have some sinusoidal form. Now, how does that look like? Well, now it's very simple. Remember I told you that we have to connect the pieces. Recipe number, the step number 2, connect the pieces. And the rule was that psi 1 at 0 should be equal to psi 2 at 0. Psi 2 at A should be equal to psi 3 at A. And then I told you we have to connect the derivatives. However, that's where mathematically this gets in trouble. You can't connect also the derivatives. You can check that if you try to connect the derivatives, you get 0 all over the place. Again, it's a small mathematical artifact. Later I will show you how, these can be fixed if this is not exactly infinity, but 10 to the 29 in every unit you prefer. So the derivative here, for this specific example only, cannot impose equality of the derivatives. Okay, but now you see that the solution is essentially trivial, right? Because if I impose this, psi1 of 0 is equal to psi2 of 0, psi1 of 0 is 0. What is psi2 of 0? Well, psi2 of 0 is A times 0. Well, fine, that part is. And then plus B, because cos of k times x with x equals 0 is 1. Well, but then B must be equal to 0. From these, we get B equal to 0. Okay? So let me do something just that we keep track. Then I can just erase this term. What does the second condition tell us? Let me also erase these now. Well, the second condition tells us that these evaluated in A must be 0. So this tells us that sine of k times A should be equal to 0. And obviously, this imposes a quantization on k. K cannot take any arbitrary value, right? Where are we? Here. If this must be the case, then k must be equal to n times pi over A for n, well, in this case, natural. The negative solution, we just put a minus sign, which is a global phase, right? So we can just stay there. And natural plus, because n equals 0, would give again the wave function that is 0 all over the place. Okay? But this is very interesting, right? Because look at what this means. K equal to that, but K was this, right? So this means, if I equate the two of them, it means that 2me over h bar square is equal to n square pi square over a square. And so this is these together with that. And, well, just rearrange the terms. You get that E is equal to h bar square over 2m, another factor pi square over a square, n square. And so you see that the solutions are quantized. So only these values for the energy will give us a solution that is continuous as we expect. So normally we write this e to the index n, and you see that it goes like n square. Okay? So this is what you want to show. And so let me summarize now. I just erase some things and put everything in place. It's all in the lecture notes anyway. So what we have found here is that, well, it's not too difficult to normalize these guys. So 2 over a sine of n pi over a times x. Oh, well, it's better, maybe it's more elegant if I write it like this. And this is the solution to nth level. This is valid for all n. And this is the eigenvector. This psi of x is the eigenvector corresponding to the eigenvalue that I just wrote down before. This strange numerical factor n square. So what does it mean on this drawing? Well, it means that maybe I should do it a little bit bigger. I will just redo it on the other side. So we have our infinite potential well. And we have the first energy will be, well, somewhere here, whatever this number is, right? Then it would be, so this is this, this would be this, E1. Then the second one will be at 4 times E1, somewhere here. The next one will be at 9 times E1, and so on and so forth until infinity. And how do the wave functions look like? Well, they look like, let's do it in red. Normally we represent the wave functions on top of the energy level. Of course, the base of the wave function is always at 0, right? So don't misunderstand. This is always at 0. But we just draw them like this. So, okay, the first wave function is 0. And then there is a sine of pi x over a, well, which is just this. The second wave function has 2 pi x over a, so it would be something like that. And guess the third, right? And I think you can guess the other ones. So this is my psi 1 of x, psi 2 of x, psi 3 of x, corresponding to E1, E2 being equal to that, E3 being equal to this. Okay? So this is the mathematically simple solution of the infinite potential well. What is instructive here is essentially that we have seen how the energy in these wells is quantized. Now I switch back to the PowerPoint presentation, and I will show you the finite potential well, which is only slightly more convoluted. Unfortunately, we see that we can't get a fully analytical solution, but we can get a lot of information about the solutions as well. So, bring down the screen, open up the presentation, and I will change the light. Okay, so now we're going to study the bound states of the finite potential well. For the diffusion states, you can find them in textbooks. And the textbooks are full of examples also of steps, of barriers, and so on. The barrier is studied in a tutorial. And I mean, the rules are always the same. And if I ask you something in the exam, I will tell you what to compute. So, I mean, you don't need to memorize too much, apart from, again, the important rules, which is solve the Schrödinger equation for each portion and connect the wave functions. Okay, so let's go. Let's set the problem. Well, in this case, I will show you, before I did it very quickly, because anyway, it was so simple. Now it's much more convenient to put the coordinates in such a way that the well is not between 0 and a, but between minus a over 2 and plus a over 2. Because now we exploit a symmetry of this well. And then again, it's more convenient, rather than putting this at 0 and this at something, to put this as minus V0 and that one at 0. Again, conventions, okay? Energy can be moved. So we are going to look for eigenstates that are bound states, meaning that the energy is below 0 now, is in this part. Of course, not down there. Huh? Now, if we exploit the symmetry, we can simplify the problem, right? So, what does it exploit the symmetry? Since the potential is symmetric by change of V of x into V minus x, then we have that if we find a solution phi of x of some shape, the solution phi of minus x is going to be also an eigenstate. So two linearly independent eigenstates. But then we can play in that basis of these two linearly independent eigenstates to say, hey, wait a moment, I will rather then play with the even and the odd superposition, right? Because in this case, phi of x plus phi of minus x is a solution, and phi of x minus phi of minus x is also a solution for the same, it's a degenerate eigenspace if you want. So we can look separately for odd eigenstates and even eigenstates. So, what are the even states? Well, the even states are of this type, right? So look up there. Again, apply our rules. For x below minus a over 2, we are below the potential, so it's a decreasing exponential. And we know already it's not going to be an increasing exponential because it would explode, so it's something of this type. Similarly, on the other side, a larger than a over 2 must be of this form. And we are looking for an even solution, so this a is the same. That's the advantage of the whole thing, right? Lambda is determined by the energy, so there's nothing we can do. But we could put in principle A1 and A2, but we're looking for an even solution that is symmetric under parity, so therefore this A is the same. In the middle, we are in a sinusoidal form, and we might want an even sinusoidal form, and that's cosine. Again, the lambda and the k's, you can check all of these peacefully, are defined as usual. Okay, so let's try to do that. These are the famous connections, so that the wave function at minus a over 2 coming from the left is the same as the function at minus a over 2 coming from the right, the same for the a over 2, the same for the derivatives, and it gives those solutions. Now you say, well, how does this come about? Sit down, relax, stop the video, compute, find it. This is a typical thing I can ask in an exam. Not exactly this, of course I will change the potential, don't worry, I will not ask you to memorize these, I will ask you to write down the equations, find the conditions, and find some condition of that type such that, that these hold, right? So please, take your time, stop the video, do it by yourself, check that this is correct. So, from these two equations, you eliminate stuff and you find that lambda is this function of k. Now, remember please, lambda and k are both function of the energy, right? Lambda was the k for the exponential, and k is the one for the sinusoidal function. In both of them, there is the energy. So therefore, this condition tells us that only those energies such that this equation is satisfied will be solutions. Unfortunately, you see, this equation is a bit messy, right? It's not something easy to solve because there is a non-algebraic equation with k both outside and inside a sinusoidal function. So we're not going to be able to write, like before, e equal to something nice like n squared. But we will see how to solve this visually. Okay, that's what I said. Remember, lambda and k are given by that. If I write u is like the k of the potential. I get lambda squared equal to u squared minus k squared. And these are the conditions under which the energy is a possible eigenvalue. We do the same for the odd states. Well, it's odd, right? So the only difference between before and after is that now I have a and minus a, and I have sine instead of cosine as the sinusoidal part. Same exercise, please do it yourself and whatever, and then you get that equation. And now I'm going to show you the solution, or at least the graphic solution. A computer can give you the numbers now. Let's go peacefully through these. The curve in red is k tangent k a over 2. Remember, this was what appeared in for the even solutions. The curve in blue is minus k cotangent k a over 2. That's what appeared for the odd solutions. The curve in black is lambda, which is u square of k minus u square minus k square square root. So remember, the even solutions were such that lambda is equal to that guy. The odd solutions were such that lambda is equal to that guy. Here I've taken these values, u equal 2 and a equal 10, just for in some units. So we see for this choice that I've taken here, how many solutions do we have? Well, the first one is here. Here, lambda is equal to the thing above. So this value of k would be the solution. Of course, now we have to change k into an energy, but it's a trivial function. Then the second solution would be this one, the third solution, that one, the fourth, this one, fifth, sixth, seventh. So for this particular choice of parameters, there would be 7 solutions in the potential well. If I draw it, let me draw it here. So what we have found, you have to extract the energy from the K, but what we have found is that there are 7 solutions, 1, 2, 3, 4, 5, 6, 7, before we somehow go out of the well. And now this is even, this is odd, this is even, this is odd, and so on. So remember what that means, right? It means that this wave function will be probably something like this. This wave function will be probably something like that. Oh, sorry. This will be something like this, and so on. Right? So very similar to what we had before for the infinite potential well. Well, if you now, what happens if you change the parameters? Well, again, these are just things that you can see that. So change the parameter means that, for instance, you can bring this intersection point back. And now you see that however back you bring it, there will always be an intersection with a red curve. So in every potential well, however shallow, there is always at least one bound state. Okay? Which is given by an intersection of this curve with that. There may not be, however, a second state, because if the intersection is the black curve falls down here, it never intersects the blue curve. Okay? So these are the kind of things that we study. This kind of analysis I may not ask in the exam, or I would ask it only for those who want to get the A+, right? Because this is, this requires a little bit of parameterization and skills and whatever. But I assume everybody should be able to solve, to put down at least the equations that must be solved. Right? So again, to write down the pieces of the wave function, write down the connecting conditions, and maybe manipulate them a little bit more to say that, okay, the lambdas and the k's and the k1 and the k2 and the k5 and the lambda 1 and however many pieces you have must satisfy these equations in order for an energy to be an eigenvalue. Okay, with this I finish this part. Maybe I just mention one quick thing, is that, again, there are other canonical, very simple studies, potential that you find in the textbooks. The one that you find in the tutorial is this, what is called potential barrier. This one is usually studied to discuss the tunneling effect. And let me spend a couple of words on tunneling. What does tunneling mean? As you know, a classical particle that would come onto this barrier with this energy, so this is not where, yeah, it could be where it is if it's gravitational, but somehow with an energy here, would not be able to pass the barrier. Now, we know how the eigenstate, or in this case, these are diffusion states. We know how the diffusion state here would look like. It will look something like this, sinusoidal here. Here there will be an exponential decay, and then sinusoidal here. By the way, the period here is the same as the period here. So then there will be another solution next to it that has the same shape. Now this means that if I come in with a wave packet that decomposes on this one, when I change the components of the wave packet, at the beginning the wave packet is all here. So there is destructive interference on this side between the different waves. When the wave packet propagates, at some point there may be constructive interference on this side. So when the wave packet comes in, the dynamics may be such that part of it comes back, and part of it maybe has managed to go through the barrier and goes through. Actually, they are very much deformed. I don't think it's so nice, as nice as this. Normally, it looks more something like this. But again, the fact that if you come in with a low energy particle, still you can pass through a barrier, this is something that classically cannot happen. It's called the tunneling effect. This is for the potential barrier. Another example is the potential step, which is just this guy. Again, only diffusion states. those that look like that, and those that look like these. And here, what people are concerned about is obviously the reflectivity. Well, in this case, the reflectivity would be 1, but here is not completely trivial. If you come in with a particle, you say, well, I'm above the potential, so nothing should happen. But because there is something here, you still feel the potential. It is possible that sometimes you find things being reflected back, even if you are. So it's kind of the opposite of tunneling, right? In classically here, you should be able to continue. Here, there might be something reflected back, even if you are above the potential barrier. Again, all these things you find in all the textbooks, so I will not spend more time on these. So we finished the lesson on piecewise constant potentials, and the next lesson is about the most important, probably dynamical system of this chapter, which is the harmonic oscillator.